Hi there, my name is Euro Morales, and I will be uh, doing this video to solve the second problem for the extra credit video number 2. And here I've gone ahead and I've written out the problem beforehand. So the objective is to show a synthesis of this molecule or mechanism that will take us to this molecule here. So to start out with, we have to notice that we're under strongly acidic conditions. Um, so we know we're not going to ever make any negative charges in our mechanism. So if we see that, we know that we've gone wrong. Um, the next thing we notice that we have a strong acid. So our first job is to find out our nucleophile that's going to deprotonate our strong acid. So looking at what we have in our starting materials, we have an alcohol, part of a carboxylic acid. So these electrons, even though they are lone pairs, they're kind of preoccupied with the resonance here in this molecule, so they won't really go out and attack. The lone pairs on our oxygen on a carbonyl group could go out and attack. But if once we work through the mechanism, we'll eventually come out with another carboxylic acid. So we pretty much don't get anywhere. It's just a reversible reaction, but it could happen. So that leaves us with lone pairs on our oxygens connected to our 5-member ring over here, which actually are the nucleophiles that we're looking for. So lone pair on one of the oxygens will come out and deprotonate our strong acid. So we will get a positive charge on that oxygen due to the protonation. So we start out with that product. So now if we go ahead and look at our starting material, we know that this ring looks really different. We don't really have this portion or this ring in our final product. So our next objective is to take care of this positive charge on this oxygen because this isn't very happy at the moment. So we know that the way that we have to do that is by collapse resonating electrons. But the driving force to break this sigma bond, there has to be a force causing that. So the resonating of our electrons to that point will drive these electrons to kick out onto our oxygen, leaving us with So that leaves us with a double bond on our oxygen, which gives a positive charge on that oxygen now. But we get our happy alcohol. So now our immediate is to kind of take care of this carbocation, which is unhappy at the moment. So again, looking at it, our electrons will resonate up to take care of that double bond. And the driving force causing that will be a nucleophile, which will attack the electron deficient carbon on this double bond, which is induced by the high electronegativity of our oxygen, causing this carbon to be partial positive. And water is our nucleophile because looking at our equation, water is present and it's really the only nucleophile here that can actually attack without creating a negative charge. So our product up to that point So our product up to this point So product to that point looks something like this. So we have a positive charge on our water that just attacked. Our electrons were resonated up to here, so we no longer have a positive charge. Now, if we go ahead and we look at our end product, we're getting closer, but we don't have this portion of our molecule present in our final product. So we know that this sigma bond has to break somehow. So we need to create a driving force, a driving force to go ahead and resonate these electrons up to our oxygen, and kicking off this group, or resonating these electrons the other way. So what I went ahead and I did is I did a proton dance. So I deprotonated with water to take care of that positive charge on the OH, and then I used my acid to protonate my oxygen, giving me okay. So this left me with now a positive charge on this alcohol, this oxygen, resolve the positive charge on the alcohol up here. So now I actually have electrons that can resonate down, which will create these electrons to kick, breaking this sigma bond, which leads me to, which will give me actually two products now, a ketone with the protonated oxygen, which has a positive charge, as well as an alcohol. So this product will eventually be deprotonated by water and just create a ketone in my solution. But what we're really interested in from this point is with this molecule, which is eventually going to create our final product. So now we need to look to see if something is going to attack from the outside or whether we have intramolecular chemistry happening. So we have to look for our electrophile. So our electrophile, our most electron deficient atom is our carbon here, part of our carboxylic acid. So it's electron deficient due to the electronegativity of the oxygen. Now we need to look for our nucleophile. So we have lone pairs on all these oxygens, which could act as a nucleophiles, but the alcohol here, these electrons are kind of preoccupied again with that resonance to the carbonyls, so those aren't going to make a good nucleophile. The oxygen here could attack, but it would create an unstable 3-4 member ring, so that's not favored, that's too high energy. So we do have our oxygen at the end, which can come in and attack our carbonyl, which is what would happen, which is what's actually going to happen. And since we know that we're making a ring with an oxygen included in that ring, we know it's intramolecular forces that's going to cause that. So if we go ahead and number our atoms, we have 1, 2, 3, 4, and 5. So we are going to have a 5-member ring with oxygen incorporated. So it's 1, 2, 3, 4, 5. On our, let's see, we have an oxygen here, so that's a positive charge on that oxygen atom. On our third carbon, we have an alcohol, so bring that over. And then on our 5th carbon, we have our carbonyl, as well as an alcohol group, but this is actually not a carbonyl yet, getting ahead of myself. This is actually a alkoxide, but we still have an alcohol there as well. So I am going to move on to the back because I ran out of room. Okay, so where we're at in our mechanism is so this is where we are at. I believe so. Yes, this is where we are at. Now to continue the problem. Okay, so to continue the problem, we have to deprotonate this oxygen to take care of the positive charge. We're going to leave this alcohol alone because that's in our final product. But this alcohol should not be present in our ring, and instead we should have a carbonyl. So again, we're going to do a proton dance to deprotonate with water or hydrogen, as well as with our acid, we are going to deprotonate. We're going to protonate, sorry. Which will give us our alkoxide with our positively charged double bonded hydrogen to our oxygen, and our positive charge on our oxygen here in our ring is gone. Now we have a good leaving group. So as these electrons collapse, this group is kicked off and we get our final product. So that is it. Hopefully it's correct. We'll see ya.